Okay, hi everybody. Today we start a new topic, which is optics, classical optics and geometrical optics. Optics is a science that deals with light. Everything related to light. Light emission, light propagation, interaction of light with matter, and detection of light. So if we talk about the sources of light, all the sources of light can be divided into two large groups. The first group is the natural sources of light. And among the most important natural sources of light is our sun, the closest star. The sun is the source of light and heat energy on the planet. Also, other stars can be seen at night. It means that hundreds and thousands of stars that can be seen with naked eye are emitting light. And this light is sometimes utilized in some experiments with light. The light from distant stars. The number of stars in the galaxy is actually much larger than we can see with naked eye. The number of stars in the galaxy is about 100 billion, and what we can see is just a small portion, no more than a few thousands. Among the natural sources of light, we can mention lightning. Lightning is also a natural source of light, but to use this source of light is inconvenient because one never knows when the lightning will come, at what time, and in what place. So this is a random source of light. If we talk about the artificial sources of light, man has created a lot of them. The first is a candle, which we can light a small fire on the end of the candle, and that was probably the first artificial source of light, apart from fire in the fireplace. And also we have a light bulb, electric bulb, which radiates light because of high temperature of its filament. And also we have some semiconductor sources of light, like light emitting diodes, and also we have lasers. Lasers nowadays are very important artificial sources of light, which are used in many experiments with light. So the light can be obtained in different situations using different sources. And how do we detect light? We have a very good detector of light that is a natural organ which is given to us, a human eye. An eye is very good, is very sensible detector, capable of detecting very small light intensities. And also human eye is very sensitive as far as the light color is concerned. A human eye is capable of detecting and distinguishing between a great lot of colors, sometimes located very close to one another. So human eye is a unique device with which we can observe light. Also, there are some artificial detectors of light, like photodetectors and photographic plates covered with photosensitive material, and some other devices which were invented to measure single quanta of light. As far as the properties of light are concerned, one should say that light is an electromagnetic radiation. It's an electromagnetic wave. And to discuss this issue, I will draw a line to show different wavelengths of electromagnetic radiation, and let this be, for example, 1 nanometer, and this will be 1 micron, and that will be 1 millimeter, and that will be 1 meter, and that will be 1000 meters, 1 kilometer. So along this line I have shown different wavelengths in logarithmic scale. Each new point on this line refers to a wavelength 1000 times larger than the previous point. 1 meter is 1000 times larger than 1 millimeter, and 1 millimeter is 1000 times larger than 1 micron. And so 1 nanometer is certainly 10 to the power of 9 meter, and this is 10 to the power of -6 meter, and that is 10 to the power of -3 meters, and that is 1000 meters. So if we talk about electromagnetic radiation, it covers all these possible wavelengths. If we consider radiation with kilometer wavelengths, then this radio waves, this radiation is used for long-distance communication. If we talk about hundreds of meters and meters wavelengths, then this is radiation for different radio stations, including frequency-modulated signals. If we talk about millimeter and centimeter radiation, this is radiation used in many devices, like in decimeter range, like microwave oven, which is used in kitchens. Microwave belongs to this region. And also centimeter range and decimeter range is the range of radiation used in radiolocation and radiolocation. And here we come to less than 1 millimeter waves. This is an infrared radiation. Infrared radiation emitted by heated objects. And then we come closer to 1 micron, and here we find the optical range of radiation. That is the optical range of wavelengths, which range from about 0.4 up to 0.76 microns. That is about 400 nanometers up to 760 nanometers. That's a short range of wavelengths which constitutes a visible light. What we can see with our eyes is the radiation having these wavelengths in this region. That is the range of wavelengths of visible light. If we go further to short wavelengths, we find ultraviolet radiation and X-radiation, X-rays. So in this visible range of light, the largest wavelength belongs to a red line. We perceive this radiation as a red line, and then goes yellow, green, and blue, and dark blue, and violet radiation, and this is ultraviolet radiation on this side, on this part. So the light radiation is a radio frequency, is the radio waves, electromagnetic waves with such a small wavelengths. So these are the wavelengths for visible light. Very important property of light is its velocity of propagation in vacuum, or speed of light. The speed of light is usually denoted by letter C, and it's about 300,000 kilometers per second. About 300,000 kilometers per second. That is the speed of light. There is a very simple connection between the wavelength and the frequency and the speed of light. So the frequency is the number of wavelengths which go in 1 second if the light propagates in vacuum. From this relationship, we can easily obtain the frequency of any electromagnetic radiation if we know the speed of propagation in vacuum and the wavelength. And as far as the light is concerned, we will find the frequency of light waves as 3 times 10 to the 5th power kilometers, and I would like to use meters in international system. So the number of kilometers must be multiplied by 1000, 10 to the 3rd power, and that will be meters per second. Meters per second. And also I will divide it by some wavelength, like let it take 0.6, somewhere in the middle of this interval, 0.6 microns. Micron is 10 to the minus 6 meters. So meters will cancel here, and what we have, 3 divided by 0.6, that's about 5. And then we have 10 to the power of 8 plus 6. That will give us about 5 to the power of 8 by 8. 5 times 8 to the power of 14. That is 1 divided by second. That is hertz. So what it means, it's about 500 terahertz, a huge frequency. That is the frequency of visible light radiation. Something about this. Some red color light will have slightly smaller frequency because the wavelengths will be slightly larger, and green and blue and violet radiation will have slightly larger frequency because the wavelengths will be slightly smaller. But that is a characteristic frequency of visible light radiation, about 500 terahertz. That is, the frequency is about 510 to the 12th power of hertz. That's the most characteristic frequency of visible light. Now we will consider some properties of light, and the first and the simplest property is the rectilinear propagation of light. If you have a small ray of light, it propagates along the straight line. And so a small ray can be obtained by allowing the light to pass through a small pinhole. And if we have here some source of light, then behind this wall with a small pinhole, we will have a light ray, and that ray will propagate along the straight line. That is a rectilinear propagation. Rectilinear propagation of light rays. That is very important and one of the simplest properties of light. Also, it's very easy to see the rectilinear propagation along the straight line if you have a small laser. A small laser any laser will give you a very pointed ray of light, which obviously propagates along the straight line. And the light ray can be seen if it's dispersed by if it's if there are some dispersive particles here, like smoke, then in the smoke the light will be the light ray can be visible. If the space is absolutely empty, absolutely nothing there, then you will not see the light ray inside the empty space. In order to see the light ray, you must have some small particles here which will be illuminated by light and which will be visible in the light ray when they are illuminated. Is this property of rectilinear propagation a universal and absolutely applicable in any situation? No, certainly not. Sometimes the rectilinear propagation of light is violated. The most simple case when it's violated is when we have a diffraction of light, on the edge of this pinhole, or on some objects like this screen. A diffraction of light causes the light waves to propagate not rectilinearly, but in some more complicated fashion. The diffraction of light will look something like that. The light propagating when it's diffracting. But in many cases, the diffraction can be neglected. That is the case when the wavelength is much smaller than the dimension of the pinhole through which the light passes, or when the wavelength is much smaller than other dimensions here which are important for propagation of light. So if we have small wavelengths, then the phenomenon of diffraction is negligible. And then, and only in this case, the propagation of light is rectilinear. Also, there are some other situations when rectilinear propagation is violated by something. For example, rectilinear propagation will be violated, the light will be distorted near a gravitating body. For example, if you have a sun somewhere here, if you have a sun, and this is the light coming from a distant star, and this is the sun, our sun, then the light rays coming near the sun will not go along the straight line, but they will somehow be distracted, deflected. But this angle is very small because the sun has small gravitation field. If we take some more stronger gravitation field of heavier bodies, then the deflection of light rays will be larger. So the rectilinear propagation will not apply if the light train goes near the gravitating body. But this is an exotic situation which is observed somewhere in outer space, and you must apply special tools to observe this phenomenon. And in our everyday life, this deflection of light waves in gravitational field can be neglected. It's very small, it's negligible. Also, we neglect diffraction in the field of geometrical optics. This condition is the condition of application of geometrical optics, the rules of geometrical optics. The wavelength must be much smaller than the dimension of all other objects with which light is interfering. The dimension like the diameter of the pinhole through which the light is propagating. So this is the general condition for applicability of geometrical optics. If this condition is violated, then you will have no right to apply the rules of geometrical optics. If this condition is violated, then you will have to use the rules of wave optics. And wave optics and wave propagation is described in general case by Maxwell's equations, by wave equation, which is a consequence of Maxwell's equations. And that is more complicated case, actually. So we start from geometrical optics. We neglect the wavelength, though sometimes even in geometrical optics, the fact that that there is some wavelength is important. The fact that light radiation has some wave properties will be important even in geometrical optics in some certain situations. The second property of light, which we will consider apart from rectilinear propagation of light rays, the second property will be reflection of light. So suppose we have a light ray which falls on the surface of some body, on the smooth surface. Then this light ray will be reflected from the smooth surface. This is a reflection. Reflection of light. There is a simple law of reflection. If you draw a perpendicular to the surface, a normal line, then the reflection takes place in such a way that the reflected beam of light or reflected ray and the falling incident ray lie in the same plane with the normal. These three lines, the incident ray and the normal to the surface and the reflected ray, all these three lines belong to the same plane. That is the first important thing. And the second important thing here is that the angle of incidence is equal to the angle of reflection. So this is the angle of incidence and this is the angle of reflection, say so. So these two angles are equal. If we observe reflection from a plane mirror or plane surface which is very smooth. If the surface is not very smooth, if it has some roughness on its surface, some rough surface, then the light will not be reflected according to this law. Then the light will be scattered. Any light ray will be scattered in all possible directions. And the scattering will take place, it will have some diagram of energy distribution, and the scattering will take place in each point of this surface. That's the way all the usual subjects around us, all the usual subjects reflect light. They scatter light. A piece of paper, any piece of paper you take is scattering light in all the directions. At whatever angle you look at it, you always see the white sheet of paper because it scatters light in each point of it, scatters light in all the directions. Because it's not a very smooth surface, it has some roughness. And the roughness is on the dimension of this roughness is of the order of magnitude of the wavelength lambda of the incident light. So if the roughness, if the dimension of this roughness is of the order of lambda, then you will have a scattering surface. But if the roughness, which is always there, it's impossible to produce absolutely smooth surface. It will always be a little bit rough. At least on the atomic scale, there are atoms here. Atoms are molecules. So at least on the atomic scale, it will not be very smooth. It will have some roughness. So, but if the dimension of this roughness is smaller than lambda, much smaller, then this surface will act like a mirror with perfect reflection. If you take a substance which is transparent, like a piece of glass. For example, this is a piece of glass. this is a glass plate. This is a glass plate. Then only part of the incident light will be reflected. Another part will go somehow into the glass. And that will be the angle of refraction. Let it be I1, and that will be I2. The angle of refraction. So this light is called refraction. This is the phenomenon of refraction, and this light ray is called a refracted light, in contrast to the reflected beam of light. This is reflected and this is refracted beam of light. The angle of refraction I2 depends on the properties of this transparent medium. And when this light beam will go out, it will again be refracted at the interface between the two mediums, between the two media, the glass, for example, and air. If the light beam goes out of the glass, it again will be refracted. And the angle here will again be I1. And that will be angle I2. So refraction on the surface of a transparent medium takes place depending on which medium has more density, more optical density. If this is a glass, then and the light beam goes from the air, then the refracted light will somehow be bent toward the normal. If the light beam goes from the glass into the air, then the refracted light will go away from the normal to the surface. And there is a simple law which governs this, which describes this phenomenon. And the law is called the Snells Law. The Snells Law uses the refraction index of medium, the refraction index n of any transparent medium has its own refraction index, which is defined, the refraction index is defined as the speed of light in vacuum divided by the speed of light in medium. In this medium, the speed of light is smaller than in vacuum. That is an experimental fact. The speed of light can be measured in the medium, and it's much smaller. Sometimes it's 50% smaller, sometimes it's twice smaller, 2 times smaller. So depending on the medium, but usually the speed of light is smaller, a few percent smaller than in vacuum. So n refraction index varies from 1 to 1.2, 1.3, 1.5, and in very exotic cases it goes higher to 2 or more than 2. Actually, it's about 1.5 or less. So this is just saying what will be the speed of light in the medium. And the Snells law is connecting the phenomenon of refraction with the speed of light in this medium. And so if suppose the speed of light here this is a vacuum, and speed of light here is c, and speed of light here is much smaller, speed of light here is v, then there is a simple law, Snell's law, which says that sine of the angle of incidence I1 divided by sine of the angle of refraction I2 equals n. That is the simplest way, the simplest version of the Snells law. Now we will derive this law. We will derive this law from some theoretical considerations. Let us consider an interface between two parts of the space, and the first part will have a refraction index n1, and the second part will have a refraction index n2. And so let a light ray fall on the interface. There will certainly be some reflected beam of light. I will not consider it now. I will consider only the refracted beam of light. And now we remember that light is an electromagnetic wave propagating in space. And the electromagnetic wave has some wavelength, and it's propagating very much like a wave on the surface of water. You can well imagine a wave on the surface of water. So practically the same happens in the space. Or you may imagine a wave of a sound wave propagating in air. So there is a wavefront. If we have a beam of light and we consider a wavelength, then it means that we don't neglect the wavelength, and we consider a small, narrow beam of light. We consider it in detail, trying to understand what happens there on the language of wavelength. So we consider this beam of light as if it were a thick beam of light, that is the whole space filled with this plane wave. And the plane wave must have a wavefront which is perpendicular to the wave propagation, and wave propagation is the light beam. So this is a right angle, and this is the wavefront, and the wavefront propagates in space with the velocity of light, and at some moment of time the wavefront will be here. And this point will propagate further and reach the interface between two media during some time interval. And if this distance is delta x, then it will be equal to the velocity of light v1 in the first medium times delta t, a time interval needed for the light wave to propagate to this distance delta x. What happens at the same time with this light wave which goes into the medium? Here we use a principle of Huygens-Fresnel, a Huygens-Fresnel principle, which says that every point of wavefront is the point of secondary waves. So when the disturbance in space, electromagnetic disturbance, electromagnetic wave comes to this point becomes the source of secondary waves. It radiates secondary waves which propagate at some velocity v2 in this medium, which is, by the way, by definition, is the velocity of light in vacuum divided by the refractive index of this medium. So we have the medium with refractive index n1 and the medium with refractive index n2. And the velocity of light here differs from the velocity of light in the upper part of this space. So here the light wave will propagate with different velocity. It means that when the light comes to this point here, inside the medium it will go to some at some different distance, so that the light front inside the medium will form at some different angle, and that will be the distance propagated by light wave from this point to this point during time interval delta t. And this distance will be, for example, let it be delta x1, and that will be delta x2. That will be, again, the velocity of light, v2, in the second medium, times delta t, where delta t is the same time interval. So during the same time interval delta t, the light propagating in the first medium will go to distance delta x1. And the same light wave propagating in the second medium will go at a different distance delta x2, because the velocity of propagation here is different. So the wavefront in the second medium will be somewhat turned by some angle with respect to the wavefront in the first medium. So the wavefront has some different direction, and therefore the light beam or the light ray in the second medium will have different direction, because the light, the direction of propagation, which is indicated by the light ray, is always perpendicular to the wavefront. Is perpendicular to the wavefront. If the angle of incidence here is I1, then this I1 angle is this one, because the light ray is perpendicular to the wavefront, and this is, by definition, is the normal to the interface between the two parts of space, between the two mediums. And so these two angles are equal to I1. Also this angle here, the angle of reflection I2, will equal to this angle. This is also I2, this one. And if we consider the sine of I1, then the sine of I1 will be delta x, by definition of sine, the opposite leg in the right triangle. This is the right angle. The opposite leg must be divided by this hypotenuse, which I will denote by A, for example. This hypotenuse is A. And the sine of the angle of refraction of this angle here, which equals to this angle, will be equal to, according to the same definition, the ratio of the opposite leg, which is delta x2, to the same hypotenuse A. So this is delta x1, certainly. If we divide one equation by another, we obtain sine angle of incidence divided by sine angle of refraction equal to delta x1 divided by delta x2, and hypotenuse A will cancel here. Now we recall what is delta x1 and delta x2. We substitute this expression here, and we obtain v1 delta t. And for delta x2, we substitute this expression here, and we obtain v2 delta t. Delta t will cancel, and we obtain v1 divided by v2. The relationship between the velocities of light in the two medium, and in the two media. And so the velocity of light in the first medium is equal to the velocity of light here equals to c divided by the refraction index n1 of the first medium. So instead of the velocity v1, I use this expression c divided by by n1, c divided by the refraction index of the first medium. And instead of the velocity v2, I will put c divided by the refraction index of the second medium. So we obtain n2 divided by n1. So if we combine the initial formula, the initial expression, with the final expression, then we obtain the Snell's law, which in the simple form was written here. I told you that this formula is valid for the case when the upper side, the upper medium, is air or vacuum, which has a refraction index equal to unity. And now we have calculated all this, everything which happens here, taking into account two different refraction media, two different refraction indexes of these two parts of space. And we obtain the same, we obtain the Snell's law in the most general form, sine 1 by sine I2 equals n2, the refraction index of the second medium, divided by n1, the refraction medium of the first medium, the refraction index of the first medium. If n1 equals unity, then you will have just the refraction index of the second medium, which is written here. So this is the most general form of the Snell's law, which we have derived based on the wave properties of light. We assumed that there is a wavefront, and we took into account and made use of the Huygens-Fresnel principle, which says that every point of the wavefront is the source of secondary waves, and secondary waves propagate are spherical waves, and they propagate in the second medium. And as every point of this interface is the source of secondary waves, all the secondary waves interfere with each other, and all the spherical waves interfere with each other, and the result of interference is the wavefront of the light beam. This is the result of interference of many, many spherical waves originating from all the points located on the interface between the two medium. So this is the Snell's law. And now we consider some interesting things which are related to the Snell's law, related to refraction. Let's consider some medium and the normal. This is the normal to the medium. And we allow for the light beam to go upward, in the upward direction, from the medium, from the glass plate, for example, into the air. So it goes from the glass plate at some angle alpha to the air, and there it will be some larger angle beta. Beta is always larger than alpha because the refractive index n here is larger than unity, and here the refractive index is unity, if this is vacuum or if this is air. And this is a glass plate, So if the light beam goes from the glass plate out into the air, then this angle beta will be larger than alpha. What happens if we increase the angle alpha step by step and send the rays at larger and larger angles? Then angle beta will also increase, and the rays here will go closer and closer to the surface. And there will be some point there will be such a ray at such angle alpha critical angle. When the reflected beam will go along the surface, it means that the refracted beam, it means that no light will go out of this glass plate. All the light will go along the surface. And if we increase just by a little bit the angle of incidence of this light beam from the glass, then all the light will be reflected from the surface and nothing will go out. This phenomenon is called phenomenon of total internal reflection. Total internal reflection happens when your angle of incidence inside some medium with large refractive index, the refractive index larger than unity. When the light ray goes here at the angles larger than some critical angle, then all the energy will be reflected and no energy will be transmitted to the air from the glass plate. It's easy to calculate the critical angle because we know the situation, the requirement that sine beta divided by sine alpha in this particular case and equals the refractive index An. But if beta equals 90 degrees, that will correspond to the critical angle of incidence of a light ray from the glass plate, inside the glass plate. So if beta is 90 degrees, then sine beta is unity. And then this alpha will be equal to critical angle at which all this internal reflection, total internal reflection happens. So this is the condition for internal reflection, for the critical angle, the condition for the critical angle. And we may say that the sine alpha, if alpha is larger than critical alpha, then sine alpha is also larger than critical alpha. So it must be larger or equal than 1 over n for the total internal reflection to be observed. We have to choose such angles alpha for the light ray going from the glass plate to the air, such angles alpha which are larger than critical alpha. And if critical alpha is defined by this formula, then for any angles alpha larger than critical alpha, sine alpha will be larger than 1 over n from this equation, and that will be the condition for total internal reflection. Total internal reflection. So we may increase the angle alpha up to 90 degrees, starting from critical angle up to 90 degrees, and inside all these angles there will be a total internal, inside all these angles of incidence from here, there will be a total internal reflection. And for this angle, the reflected light will go this way, and for this angle, the reflected light will go along this way. But all the energy will be reflected into the glass, and no light energy will go into the air, if the condition is this one. And certainly, sine alpha must be smaller or equal to unity. It can never be larger than a unit. So the second property of light we considered was the reflection and refraction. which is described by the Snells Law. And total internal reflection is property number 3, which we considered here. And property number 4, which I would like to underline, is the dispersion of light. The dispersion of light is the property which consists in the dependence of the refractive index on the frequency of light. The refractive index n, which actually depends on the velocity of propagation of light, actually depends on the frequency or the wavelength of light, because the light of different frequencies has different velocity of propagation in any medium but vacuum. Only in vacuum all the frequencies propagate at the same velocity c, the velocity of light. All the frequencies have the same velocity. But if you go into the medium, then the velocity of propagation will depend on the frequency. And so, therefore, the refraction index will be a function of frequency. If the refraction index is a function of frequency, then what do we have here? The refraction index is a function of frequency of the falling electromagnetic radiation, be it a light or be it a X-ray radiation, X-ray beams, or be it a millimeter wave, infrared radiation, any type of radiation. If you consider the dependence of refractive index on frequency, you will have some function. It's not constant. It's some function. So what happens if we direct here a beam of light consisting of many frequencies, like a white color, like a white beam of light? So this is a white beam of light. The white light is a very peculiar thing. It seems that the sun radiates the white light, and if the white light comes to the surface of some medium which has a refractive index, this is an ordinary medium like a glass, for example, its refractive index will be a function of frequency. And so different frequencies will be refracted at different angles. Some frequencies will go here, other frequencies of light will go in this direction, and other frequencies of light will go in this direction, etc. So the angle of incidence is the same for all frequencies. We have a beam of white light. But different frequencies will have different angles of refraction. Some will have this angle of refraction, others will have this angle of refraction. And it means that at different directions here, we will have different frequencies of light. And this one will be a red. We will perceive this, this ray of light as the red. Then we'll go yellow and green and blue, and then violet light, and then ultraviolet goes. And here we will go infrared, which we don't see. We don't see infrared. We can't see with our eyes infrared radiation, but it is there, and it can be detected by special infrared detectors. We don't see it, but it's there. So different frequencies will go at different directions, and we can observe all these different colors of light. Each color corresponds to different frequencies. Different frequencies correspond to different colors of light. So we have a dispersion of light. Light is dispersed into different colors, and this is the principle of work of a prism, which separates white light into colors. And the dispersion of light in a prism is well known to you. This is the reason behind different rainbows and rainbow-like colors behind the prism. If you look at the sun through the prism, or look at the electric bulb through the prism, you will see all different colors from red to blue, from red to blue, and this phenomenon is called a dispersion of light. A dispersion, sometimes it's very useful if you want to see the spectrum of the original beam of light. If you have some radiation and you want to know the spectrum of radiation, then you need to use some dispersive media. A dispersive medium is the one whose refractive index is a function of frequency. If you use such a dispersive medium, then you can see the spectrum of the falling light, the frequency spectrum. But sometimes, so in this case, if you want to study the spectrum, then this is a very useful phenomenon. But sometimes this phenomenon is not useful, it's harmful. For example, when you have a lens and you want to observe an image of some object in the lens, and you illuminate the object using white light, and the lens will give you several images. The lens will give you a blurred image which will have some different colors. It will not be a single distinct image. It will be a bad image, distracted by the phenomenon of dispersion. So in this case, the dispersion is bad, and it should be eliminated somehow. And this phenomenon of aberration of lens, a color aberration or dispersive aberration, should somehow be dealt with if you want to obtain a good image. So in some cases this phenomenon is useful and it's used to study spectra, but in other cases this phenomenon is harmful. It's an obstacle to observing a good image, and so in some cases we must get rid of this phenomenon. Somehow we must compensate it. But you must always keep in mind that there is the possibility of dispersion of light. If the light has several frequencies in it, the content of frequencies is complicated, then with complicated spectrum there will be a dispersion which may be unwanted phenomena in your experiments. The next thing I would like to consider after property number 4, probably we will solve some problem better. Better we solve some problem. So the problem will be this one. We have an incident ray of light, and it falls on the surface of some refractive medium which has a refractive index n. And so there will be some reflected light and some refracted light. And the problem says, what must be the angle of incidence if the reflected light and the refracted light propagate at the degree 90, at 90 degrees to one another? Well, my picture is not very good. My picture is not very good because it doesn't show the 90-degree angle, so I will draw it in this way. Yes, something like that. The reflected light and the refracted beam propagated 90 degrees to one another. These two beams of light are directed at the right angle. And the problem asks, what should be the angle of incidence, I1, so that this is realized, this situation is realized, so that the reflected beam propagates at 90 degrees to the refracted beam. So this will be I2. And this angle of reflection certainly equals the angle of incidence. According to the law of reflection, the reflected beam and incident beam go at equal angles, which is not obvious from my picture, but nevertheless these are two angles are equal. And we must find this angle I sub 1 such that these two beams of light propagate at 90 degrees at right angle to each other. So, what do we know about this situation? First of all, certainly we know the Snells Law, which is applicable in this case. So sine I1 divided by sine I2 equals n if the refractive index of the upper part is unity, which is the case here. So this light beam comes from vacuum or comes from the air and goes into some medium with the refractive index n. This is the first thing we know. And second thing we know that this angle is 90 degrees. How can we describe this angle? Well, this angle is the sum of alpha and beta. So we know that alpha plus beta, these two small angles, is 90 degrees or pi over 2. Alpha equals 90 degrees, which is this angle, pi over 2, the right angle minus I1. And beta equals, again, the right angle minus I2. This is always true, but in this particular problem we have a condition imposed on angles alpha and beta. We know that these two beams of light propagate at right angle. This angle is 90 degrees. This is given in the problem. So if it's given, we add these two equations and obtain alpha plus beta. Alpha plus beta will equal pi minus I1 minus I2. And this alpha plus beta must equal to pi over 2, according to the statement of the problem. So from this equation, we obtain that I1 plus I2 equals pi over 2. I1 plus I2 must be equal in sum, after adding these two angles, must be equal to 90 degrees, which is not obvious. It's not directly obvious that this should be so, but we obtained this condition from very simple algebraic conditions imposed on the angles. If this is so, then what is sine I2, for example? Sine I2 will be equal to sine the right angle pi over 2 minus I1. And what is a sine of any of the 90 degrees minus any angle. That will be a cosine of angle I1 according to geometric the properties of this geometric of these functions. So sine I2 equals cosine I1. And we use this property here, so this will be sine I1 divided by sine I2, which equals to cosine I1. And what is sine divided by cosine? This is tangent of I1, the same angle. So we obtain the condition, we obtain the solution in this problem. The problem question was, what should be the angle of incidence? We have found the angle of incidence should be such that the tangent of angle of incidence equals n, the refractive index of the second medium here. The refractive index of this medium. If we direct the light beam at such an angle of incidence, the tangent of this angle equals the refractive index of the second medium, then the reflected beam of light will propagate at 90 degrees to the refracted beam of light. This angle will turn out to be 90 degrees. Well, after solving this problem, I would go further with the properties of light. And now, after considering dispersion, I would like to consider such a simple optical device as a lens. So we have fact or property number 5. Interaction of light with lens. What is a lens? Lens is such an object which is made of glass or some other transparent material which must be solid and transparent. And usually we use materials with high index of reflection. It must be as high as possible. It must be larger than unity, and we use as large index of refraction as possible. Because if we use the index of refraction close to unity, then the lens will not work. It will work badly. If it's filled with air, it will not work at all. So the index of reflection must be the larger the better. And this object, this body, is formed of 2 spherical surfaces. One spherical surface will have a radius of curvature r1, and another spherical surface will have a radius of curvature r2. So the lens is fabricated in such a way as the lens is formed by 2 spherical surfaces. In general case, they may have different radii of curvature, but sometimes the radii are the same, or sometimes people produce such a lens which has one surface is flat and another surface has some radius of curvature r. Sometimes we have such lenses, and sometimes we have this construction of lenses. So this lens is called a convex lens. Convex, which means that the surface is convex. And here we have 2 convex surfaces. So this is double convex lens. Sometimes people produce lenses with concave surfaces. Concave surfaces with some radius of curvature. And so sometimes lenses are different. Sometimes lenses have one spherical surface, concave surface, and another surface is flat. And sometimes people even produce lenses which have one concave surface and another convex surface. So all possible situations are realized in practice. What are the properties of such lenses? I will draw a lens which is a concave lens, and it's usually people agree to denote the concave lens as such a double arrow. A theory of lens in general cases is a complicated mathematical theory, but the theory turns out to be very simple if we assume that the lens is thin. It's very thin. Its thickness here in this direction is much smaller than the diameter of the lens. So we will consider only thin lenses. Each lens has an optical center, and if we draw a line perpendicular to the lens plane, then that will be a principal, that is called a principal optical axis. A principal optical axis. The lens has this property. If we draw any line which goes through the center of the lens, then the light propagating along this line will not be deflected by the lens. It will go on propagating along the same line, along any direction going through the center of the lens, along the principal optical axis or along some auxiliary optical axis. The light will propagate without being deflected, or the angle of deflection is zero, it's better to say. Because the lengths are very thin, the light will be somehow shifted sideways, but this is negligible. This effect is negligible because it's very thin. We consider only thin lenses. Also, there is another property of lens. If we direct a light beam parallel to the principal axis, then the light beam will be deflected somehow and will go in a different direction. But all the light beams parallel to the principal axis will be deflected in such a way that they will go through the same point. And this point is called a focus. And this length, this distance from the focus to the optical center of the lens, this distance is called a focal distance. Focal distance, or focus. This is a focal point, and this is a focal distance, or simply a focus of the lens. If we choose to look at the rays, at the light rays going at the edge of the lens, if the light ray goes at the very edge of the lens, then actually this light ray will be deflected and will go somewhat near the focus, So in order to direct all the light rays into the focus, the lens must not be an ideal spherical surface. But this is a complicated thing, and we will not consider these details. And what we have to take into account that if the light rays, which we consider, go closer to the principal axis, then all of them will be focused into a single point with high degree of precision. And the discrepancy in different points where the light rays are focused will be very small. If the light ray goes away from the principal axis, then the point then its focal point will somewhat shift here. But this is very small effect, and we will neglect it. And in the first approximation, which is very good, we may say that all the light rays going in parallel to the axis, to the optical axis, and which all the light rays which are located not far from the optical axis, all of them will be concentrated, will be focused in one point, which is called a focal point. And these light rays which go not far, which are separated not far from the optical axis, from the principal optical axis, all these light rays are called paraxial. Paraxial. The word paraxial means that all of them are parallel to the principal optical axis. That is first thing. And second, they go close to the principal axis, with this distance not very large, much smaller than the diameter of the lens. We don't consider light rays which are located at a distance from the optical axis comparable to the radius of the lens. We don't consider such light rays because their propagation is described by a more complicated formulas. So as far as the paraxial light rays are concerned, all of them will have one focal point where all these light rays concentrate. And the focus of such a lens may be calculated using the formula n-1, where n is the refractive index of the material from which the lens is made, and divided by radius of curvature of one surface of this lens plus the radius of curvature of the second surface of this lens. If the lens is plane convex, one surface is plane and another surface is convex, then the plane surface will have infinite radius of curvature, and infinite radius of curvature will give you 0 for the second term here, and then only one radius of curvature will be taken into account here. Only one radius of curvature for plane concave lens. You can find the derivation of this formula in the Landsberg course of elementary physics. The derivation is not very complicated. It's simple, but we will not waste our time on this. We will better consider for the remaining minutes we will consider another important question, which is a lens formula. So if we have a lens with some principal optical axis, and there is a focus of the lens here and another focus on the opposite side of the lens, these are two equal distances, the two focus. It can be easily proved that the two focal points are located at the same distance from the lens. Then if we take some object here, I will put it like a small arrow, then how do the rays scattered by this object move, and how do they propagate in space? The object is illuminated, and so each point of this object is a source of secondary light. And the light from this point, for example, goes in all different directions. But we choose only one direction which is convenient for us. We know that any light ray going through the center of the lens goes without deflection along the straight line. This is the property of the lens. And also we know that any light ray going parallel to the principal axis will then be deflected to the focus. So this is the focal distance, and this is the same also the focal distance. So this light ray will go in this direction. And when these two rays intersect in space, that will form an image of this point. So the image of other points of this object can be drawn, can be obtained using the same geometrical construction, And so we come to conclusion that there will be an image of this object formed in the space. If this is a true object, which is scattering light, then this is not an object. This is an empty space, but just all the rays going from this object through the lens will form here an image, because all of them will be concentrated. All the rays from this point will be concentrated in this point, and so on. All the rays from this point, for example, in the center of this object, will be concentrated and focused in this place. So there will be an image of this object here. If the object has height h, the image will have height, say, h prime. And if the object is located at a distance a from the lens, then the image will be located at a distance b. And we can immediately write that h divided to h prime equals to a divided by b. Because these triangles here are similar, and this angle equals to this angle. So these two right triangles are similar, and h divided by a equals to h prime divided by b. That is the first thing which can be said about this image. And the second thing is that this angle equals to this angle. And therefore, if this is a focal distance, then this section equals to b minus focal distance. And so in this, for these two triangles, this side will also be equal to h. This is also h, and we can say, and we can write down that h divided by f from these two similar triangles, h divided by f equals to h prime divided by this side, which is b minus f. And from this equation, h equals h prime a over b. And this expression can be substituted here. So what we have instead of h, we can write h prime a over b, and divided by, yes, a over b, that was h, and divided by f, certainly. Now I take this expression, this formula, I can cancel by h prime, and what will be here in result? bf will be equal to a times b minus f. I canceled by h prime and obtain, and I multiply by bf. bf will go here, and I multiply by b minus f. It will go here, so a times b minus f, that's correct, and bf is here. After opening the round brackets, I will obtain ab minus af, and then I will have f times a plus b from here, a times b, a plus b equals ab. And that will lead us to a formula f equal to ab divided by a plus b. Also, this formula is often written in such a form that 1 over f will equal to 1 over a plus 1 over b. This is the lens formula which connects the focal distance of a thin lens and a, the distance of the object from the lens, and b, which is the distance from the image of our object from the lens. The distance of object and the distance of its image from the center of the lens are connected with the focal distance of the lens. Now it's the end of this lecture, and we will continue discussing all these sort of problems next time on the 31st of December. That will be the last lecture in this course of Introduction to Physics. On the 31st of December, as usual, we will have the last lecture, and we will finish discussing problems in optics. Until then, goodbye now.